Imagine this wind, but 180 million years ago. 180 million years ago, Red Rock in Las Vegas, Nevada would have been a vast desert with rolling sand dunes, very similar to today's Sahara Desert. But how do I know that? Just my superpower as a geologist, I guess. But actually, how do I know? How do sand dunes become petrified? What causes the reds, pinks, yellows, and whites in sandstone? What are these rock pimples? That's what I'll get into today. It's really, really cold today. It's super, super windy. I'm glad I brought my heavy coat. I've become a weakling. All of the sandstone you see here, known as the Aztec Sandstone, used to be sand dunes. The way I can tell is, for one, the virtually pure quartz sand grains are well rounded with no clay or silt. Another diagnostic feature is the crossbedding. We've probably all seen fossilized footprints. Crossbedding is like a fossilized footprint of a sand dune. It shows you where ancient sand dunes traveled and in what direction they traveled. At Red Rock, we frequently see a haphazard arrangement of crossbedding, indicating the force pushing the sand dunes was variable in intensity and direction, most characteristic of wind-driven dunes rather than water-driven like in an ocean environment. Okay, cool. That's how we know there was a desert here 180 million years ago. But how did that sand turn into what is now known as petrified dunes? The sand dunes were buried by shifting sands and other sediment as winds changed direction and intensity. Over an extended period of time, the force of overlying sediment compressed the sand dunes. Then water traveled through the sand grains, leaving behind iron oxide and calcium carbonate, which acted like a glue to cement the grains together. This process is called diagenesis, and it's how sedimentary rocks are formed. Now on to color. The black that you see behind me is known as desert varnish. It's a chemical weathering feature caused by the influence of manganese and clay minerals. I'm almost to the top. That was a tight squeeze. I made it to the top. And I'm glad I did, because I found exactly what I was looking for. Off in the distance, can you see that distinct line between the white and the red? Yeah, that's what I was looking for. What causes this crazy color difference? Well, in certain circumstances, that would be called a contact, or you have two distinct rock bodies touching each other. The red sandstone shows that you have iron in the rock that has been oxidized. The white sandstone could indicate that there is iron in the rock, but there has not been contact with oxygen to make it red. When you see contacts like this, oftentimes the white rock formed while it was underwater, like in an ocean environment, while the red rock unit formed above water, where the iron could react to oxygen in the atmosphere. But in this case, that's not what happened. It's a bit more complicated than that. This color change happens within the same rock unit, meaning this color change happened after lithification. We also know that this environment was a desert, where the sand would have been in contact with oxygen and oxygenated water, turning the white sand into red sandstone during lithification. The oxidation of iron minerals can occur before, during, and after lithification, and is further influenced by weathering. Will all of the sandstone turn red? No. Like you see here, not all of the sandstone will turn red. Sometimes this happens because iron minerals never existed in the sandstone, and other times these minerals can be completely lost through a process called bleaching. Sandstone is porous, kind of like a sponge, so it allows water to flow through it. This water can either oxidize the iron minerals if they exist, or they can actually dissolve the iron and carry it away. When I first learned this, I was incredibly confused. How can water cause both? Great question. If the water in question is oxygenated, it will oxidize the iron minerals, turning it red. However, if the water is reducing, that is not oxygenated, like a weak acid, hydrocarbon, or fluids with hydrogen sulfide, what you find in hot springs, it can actually dissolve the iron, and the reducing water can carry the iron away. This can give rise to that drastic color difference we see here. Water flows along the path of least resistance, sometimes giving rise to red and white striping where the water did and didn't travel. When that reducing water eventually meets oxygenated water or organic material, the iron precipitates out of the water and can form red bands or spherical nodules known as concretions, like this. Concretions, or rock pimples as I like to call them, are thick iron oxide coatings around a nucleus that are more resistant to erosion than the surrounding sandstone and range in size from pea to baseball sized. The mixing of the reducing and oxygenated water can also give rise to new minerals that cause the other colors we see, the pinks, purples, and the yellows. These colors can also be attributed to varying iron concentrations in the rock. Hematite is the most common iron oxide and is responsible for the reds, browns, purples, and pinks. Goethite is another common iron oxide that gives rise to yellow browns and reds. Both minerals can be formed from ferrihydrite, a poorly crystalline iron mineral that forms from rapid hydrolysis and oxidation and is often found in aqueous environments. The transformation of ferrihydrite to hematite or goethite depends on pH and temperature. Low pH favors goethite, while neutral pH and high temperature favor hematite. Yellow and brown is often associated with the aptly named limonite, which is a hydrated iron oxide. Okay, that was a lot. To recap, we learned that sand dunes become petrified through a process called diagenesis and become sandstone. Sandstone turns different shades of red and brown when oxygen interacts with iron minerals in the rock during and after lithification. Sandstone can also turn white when reducing fluids flow through it, dissolving the iron minerals like sugar and water. And concretions are basically iron-filled rock pimples that form when the iron minerals precipitate from the reducing water. Did I miss anything? Oh, I did. There's a difference between the white we see here and here. The white we see here is a deposit of calcium, which was brought probably from rainwaters carrying calcium. As you learn, the porous nature of the Aztec sandstone allow water to pass through it. The water percolates into the porous sandstone, making little cracks in the rock. And those cracks get bigger and bigger until pieces of the sandstone get pried off and turn into the boulders we see here in the canyon. That's why you will see many signs around the area warning rock climbers not to climb after it rains. Underneath the Aztec sandstone is the more impermeable Chinle Formation, which is a mixture of shale and mudstones. This impermeable layer doesn't allow the water to travel further into the ground, so it emerges at the base of the Aztec sandstone as springs. Above the 180 million year old Aztec sandstone, there is the Bonanza King Formation, which consists of limestone that was deposited 500 million years ago when this area was the ocean floor. Now, if you're paying attention, you might be thinking, How are 500 million-year-old rocks sitting on top of 180 million-year-old rocks? Normally, younger rocks sit on top of older rocks as sediment builds up over time. But not here. Las Vegas has a volatile history of faulting and folding caused by tectonic activity. The fault that has caused these layers to act weird is called the Keystone Thrust. 65 million years ago, compressional forces in the crust caused a tear, pushing the old limestone over the younger sandstone. Here you can see the Keystone Thrust Fault, which is a true contact.
Directly in front of me, you can see the Keystone Thrust. Right here. Right here, you have the 500 million year old limestone. And then under that, you have the about 180 million year old Aztec Sandstone.
Well, I think that about covers it. I hope I answered all of your questions about petrified sand dunes. But if I didn't, leave your questions down below in the comments. I'll see you next time.